So, shall we start? Hi, everybody. So, last time we talked about the PCA algorithm, right? But unfortunately, we could not finish it up. So, I just want to finish the derivation today, and then we're going to get some examples and applications. So, it's going to wrap up the whole PCA part. So just a quick recap what we did last time. So you remember that what was the key problem, right? The problem was to reduce the dimensionality, right? So what we wanted to do, we had this x, and x is in general d-dimensional, right? And this d-dimensional x, you want to just compress it into one z, and this z is significantly smaller. It's k-dimensional, right? And then we talked about this, that if we want to do everything linear, then the best idea is to do this, right? So you get x, you subtract it from some bias. That's not an important thing. Then you're going to project it using u, right? And this u is going to project your d-dimensional vector into a k-dimensional vector, right? So this is the way that we compute z. We call z to be the latent variable. Why latent? Because you have your x. You would say, I assume x has like this small representation, which I cannot see it, but somehow, or I cannot understand it directly, but it somehow contains all the information. Now, if you want to get back, so if you want to do decompression, we can do it this way, right? So we get u, and we just use it again as the basis to just construct some d-dimensional vector out of it. We could potentially add a bias if we had any at the first place, and then this is going to be the decompressed version of our sample or data point. Now, we could interpret this guy as a learning problem. We said this is the learning problem. At the end of the day, what is the thing that we want to learn? What do we want to find out? U and mu, right? The u and mu are the things that we want to find out. So we have this data set. It contains lots of samples. Out of looking at them and assuming this particular model that our latent is linear or decompression is again linear, now we want to find out what are the right choices of u and mu. And we define the right choice of u and mu to be, what was the best choice for u and mu, theoretically, was the one which makes the recovery error minimum, right? So we called it like minimal representation error. So you basically say that this x hat, which is the decompressed version, computed out of z, this should look like x as much as possible, right? And then you compute the difference between them for every single possible point, and then you are going to collect all those errors. This is going to give you the aggregated error. You want to minimize this guy, right? So that was the idea. Then we found what is the optimal choice of mu, right? That was quite simple. You need to set it to be the centroid of your data set, right? So you just get all data samples, you average them. This is the central point. That center point, that sample mean is going to be your bias, right? And for choice of u, we took quite some time to understand that if we want to choose the right choice of u, instead of going ahead and minimizing the recovery error, we could instead maximize the variance, right? And the variance was basically this one. This means that the representation that you get for every single point inside your data set, so x1 going to be compressed as z1, x2 as z2, and so on till the last one. Now you want these guys together. If you just compute the sample variance in this form, you want the sample variance to be maximum, right? Somehow containing the most possible energy. And the reason was, I mean, we did some basic linear algebra to conclude that maximizing this one is equivalent to minimizing the recovery error. Everybody's cool? Yes?
Could this be seen as like our compressed state being able to express as much as possible?
Somehow, yes, as much as possible energy, right, right. And this means that it's containing as much as possible about the data, right? So it's pretty much the same thing intuitively, but you need to be a bit concrete, and this was the one we did last time, right? Okay. And we said why we call it variance, right? Because if we look at every single zn squared, This is essentially the compressed one minus this, mean average, average sample mean on the data set. And because of that, this term that we have is essentially the variance of our representation on that particular data set. But anyways, I mean, you don't really need to remember every single detail. The key thing is that we want to just minimize this guy, maximize this term now, right? So, and this is what I told you. I try to compactly explain that if you want to do this, you essentially need to set all of the vectors inside U to be the largest, or the eigenvectors corresponding to the largest eigenvalues. I want to show you today exactly how it means, and also give you a bit of feeling in terms of, say, a data set when you look at it and you, for example, look at the spreading, it's spread over the axis. So, first thing first, I think we talked about it quickly last time. So what if I want to, sorry, not this one, here, sorry. What if I want to maximize that term? So for now, let's first just assume that our z is just single, it's one-dimensional. It has just one dimension. This means that k equals by 1. So every single data sample that I get, it's going to get multiplied by some u, which is a vector, the inner product, the dot product, and it's going to give me one number. That number is my compression, right? So z is essentially u multiplied with this guy, right? And this guy, xn minus mu, this is basically xn minus its, oh, that mu should not be here. Sorry, typo. Just remove it. So this is the mu, right? So just remove it. This happens when you copy paste. So this should be x minus the sample mean, and then x minus sample mean, it means like you're just finding the distance to the centroid for every single guy. So that is what I call it x tilde, the centralized one. It's going to make the notation much easier, right? So what we are doing, we are essentially computing the dot product between our vector u. This is the thing that we want to find out what is the best choice for it. And x tilde is the data sample that is centralized, right? This is Zn. And Zn squared is basically this guy multiplied to itself. I can write it down ux or xu, it doesn't matter, right? It's an inner product, right? So I'm going to write it down in this form. Everybody's cool? So one sample variance term, Zn squared. This is the sample variance. This one is this guy, right? Now, what do I want to maximize? I want to maximize average of this guy, right, over my data set, correct? So I want to just average it over all possible samples inside the data set and maximize it. So this means that I want to maximize this term, right? 1 over n, summation of this term, right? And I am going to replace exactly the same thing that I had in the previous slide, okay? Everybody's cool? Look at the first line. It's just the same thing, right? Now the second line, this summation 1 over n, is going to go inside because u is not depending on index, right? If you change your data sample, you don't change u, right? U is going to be the same thing forever, right? So that is coming out. And now I am saying that this guy in the brackets, I can write it down in this form, okay? And that x tilde that you see, the large matrix, is essentially this guy. So this means that I'm getting all of those centralized samples, x tilde 1 to x tilde n, and I put them inside one matrix. Everybody sees that if I multiply this x tilde to its own transpose, I'm going to end up with this expression. Everybody sees that? Yes or no? Everybody agrees? No? Okay. So seems good, right? Cool. Okay. So now what is happening here is that the term that I want to maximize, this guy, is depending in terms of u in this form, right? U transpose some matrix times u. And that matrix is this one, right? 1 over n x tilde transpose, right? This is what you call it the covariance matrix of your data set. And anyone has the idea why this is a covariance matrix or sample covariance? What is the covariance of one random variable? First of all, if you have a covariance matrix, this means your random variable x is a vector, right? This is a vector. If I want to compute its covariance matrix, how can I define it? Anyone knows the definition of covariance? Covariance is the extension of variance when you have a multidimensional variable, right? What is the variance? If x was a scalar, how do I compute the variance? Please? X minus its mean first, right? So the expectation of x, right? Correct? Then you take this guy, you square it, right? And again, you compute the expectation. This is the variance, right? Correct? Correct? Okay. Now, if I have I can write down instead of a square, I can write it down again, the guy times itself, right? It's the same thing, right? When it's a number multiplied by its own is a squared. Everybody agrees, right? Now, when it's a vector, then you cannot simply multiply. You need to define a multiply, right? So it's either dot product, but dot product going to get a d-dimensional vector and reduce it to a number, right? It's not a good idea. You want to contain the dimensionality. So what is the other choice? To do the outer product, right? So this guy is d-dimensional. You outer product it by itself, and then this is going to be your covariance matrix. Everybody's cool? Questions? So if x is d-dimensional, so this means that this guy here is one d-dimensional vector. This is d, right? Then this guy transpose is going to be again a d-dimensional vector, but row-wise, right? And then you are multiplied in d by 1 times 1 by d. This is going to be, at the output, you're going to have the covariance matrix. And this guy is d by d, right? Everybody agrees? Everybody's cool? Now, if I want to compute this expectation, so you remember I told you whenever you see an expectation, you should think in terms of the data set you have, right? You have samples, you don't know the distribution. How do you approximate this guy? You just do sample mean, right? You have the samples, so you average over the samples, right? So instead of this expectation, I'm going to write it down 1 over n, summation over n, xn, right? Again here, 1 over n, summation over n, xn, right? Again here, I'm going to have 1 over n, summation over n, right? And every single guy here, xn. Everybody's cool? Yes? Yes or no? So this guy that you see here, if you look at the previous slide, you see that this expression inside, 1 over n, this is the sample mean, right? 1 over n summation, right? And x still, every single of them is exactly xn minus this average, right? Right? So this guy that you see inside is actually approximation or estimation of what I wrote on the board if instead of 1 over n summation I have expectation, right? And this is why you call it sample covariance, because this is the way that you can approximate the covariance matrix of your process from the data set that you have. Everybody's cool? Yes?
I have a question about the intuition for this. Is it like so I understand the covariance in one dimension, it's like the difference from the mean. For this, is it the difference from the mean in all the dimensions?
Right. Yeah, you have one diagonal in this matrix that is basically the variance of every single entry you have, right?
Okay.
And then the off-diagonal entries are how they are correlated.
Oh, okay.
Yeah?
Oh, I understand.
Does it make sense?
It makes
Yeah?
sense.
No. Okay. Questions? So if it is diagonal, this means that you have every single entry is independent, right? If it is if it is not diagonal, then this means that the entries are correlated. Okay, so this is the sample covariance matrix, and what you have, what you want to do, you want to essentially maximize this guy. U transpose sample covariance times U. Okay? So sample covariance matrix is just computed from your data set. It does not depend on you. The only thing that you want is to maximize this guy. And anyone knows how you can maximize this term? Or what is the maximum term value for this term? The maximum value for this term is the maximum eigenvalue of that matrix sigma. Now, what is the reason? The reason, I'm going to explain it next, but let me first give you a bit of rough idea what is happening here. So you remember this example when I started with. So I told you if I have every single number every single point in my data set to be on this line, right? Then you can easily compress it by one number, right? And that number was simply the distance from the origin, correct? Now, let's say this is your data set. And I put this data set on purpose because I wanted the mean value to be 0, okay? So you see the points inside your data set, -2, -2, -1, -1, 0, 0, 1, 1, 2, 2. All of them are on this line, right? Everybody's cool? And now, if you average these points, it's going to be 0, right? So if it is 0, then x tilde and x are the same thing, right? X tilde is x minus 0, which is the same thing, right? Now, if you get this matrix is 2 by 5, right? It has 5 samples. 2 is the dimension of every single point, right? If you compute x times x transpose, what would be the dimension? 2 by 2, right? And that 2 by 2 is the approximation, if you average it, is going to give you sigma, and that sigma is going to be the approximation of the covariance of this process, okay? Everybody's cool? Yeah.
Why do you say approximation?
Because the true one is only known when you have the exact distribution of x, right? So if instead of this sample mean I have the exact expectation, so I multiply it to its to the probability measure, and then I integrate with respect to some dominant measure, then this is going to be the true expectation, right? But we don't know it. We can only approximate it. No. Question? Okay. Now, if you get this matrix, you compute sigma, and then you do the eigenvalue decomposition that I told you last time, you're going to end up with such decomposition. And look at this here. You have 2 eigenvalues for this matrix, this sigma. Can you tell me what are the eigenvalues? 20 and 0, right. 20 and 0. Now, one of them is 0. What does it say? Well, that guy is probably doing nothing, right? And now, if you just plot the vectors here, so you have 2 eigenvectors. One of the eigenvectors is this guy, 1 over the square root of 2, 1 over the square root of 2. The other one is the guy which is orthogonal to this one, minus 1 over, or I guess this one is the better one, right? Yeah, I guess I do it like this. No, that's right. Minus 1 over the square root of 2 and 1 over the square root of 2, okay? These are orthogonal because if you dot product these 2 vectors, this is going to be 0, right? Now, if you think of them, one of them is this one. This is the one which has eigenvalue 20. And this is this one which has eigenvalue 0, right? Everybody's cool? Yes? Questions? No question? So these are the eigenvectors, right? And you see that if you want to maximize or if you want to choose the right choice of u for this particular example, which one do you choose? What is u? This is going to be exactly the blue eigenvector, right? Because this is exactly lying on the line that you want to make, right? Everybody's clear? Everybody's following what I'm saying? Yeah? I tried to show it next, but I want you to first have the understanding, right? So the key point here is that when I had this data set and every single data point was on this line, when I compute the sample covariance and then I decompose it, I'm going to get two eigenvectors. And one of those eigenvectors is exactly lying on the line that I want. The other one is orthogonal to that, right? The one which is lying on that line is the guy who has the large eigenvalue 20, right? And the other one, which is orthogonal, is the one which has eigenvalue 0, right? So what does these eigenvalues tell you? The large one is telling you this is the direction all the data is lying on. The eigenvalue 0 tells you this is the direction no data is lying on, right? So if you want to choose one direction, which one do you choose? The one with the larger eigenvalue, right? Now, this story is going to be the same if you go for a more general case, something like this one. Now, in this case, your data is not lying on one single line, right? Your data is spread in this two-dimensional space, right? But if you want to choose one direction, which direction do you choose? Blue one or the red one? Blue one. Why? Because this is where most of your data is spread, right? So if you take this direction, then probably the error that you get out of approximation is quite small because it's going to be the distance that this point has to this line, right? Whereas if you take this one, then there are lots of points that are far away from this line, right? Everybody's clear? Now, if you compute the sample covariance out of these samples here, and you decompose it, you're going to get two eigenvectors. Again, one of them is the blue one of them is the red one. And the one which is blue is going to have larger eigenvalue. And that eigenvalue is telling you most of data is spread here, right? The smaller one is telling you that the data is not too much spread here, right? Now, if you want to choose one of them, which one you choose? The big one, right? So that's going to be the same story for our problem as well. So if you want to be a bit concrete, and I'm not, because I do not have too much time, I don't want to complicate things for you, just give you the hint, and if you are interested, you can double check it at home. If you decompose your sample covariance matrix, it's going to look like this. So you're going to have d different eigenvectors, and the reason is that your sigma is d by d, right? When you have a d by d matrix, you have d different eigenvalues, d different eigenvectors, right? And as we talked last time, you can decompose your matrix in this form. One thing that you can easily check is that this guy, by definition, is positive semi-definite. This means that these lambdas that you see here, all of them are either 0 or positive. They could never be negative. It never happens. You can prove it. Just check it online. You're going to see it. It's one of the probably assignments you get when you have stochastic processes or probability theory. So this is guaranteed that these guys are all positive, right? Now, the next thing that you can do, you would say, okay, I wanted to maximize this term, and we found out that this term looks like this. You can get this u, and you can multiply it from here and also from here to these matrices, right? And then you can do a bit of calculation. You're going to end up with this term. So this is going to be the summation eigenvalues multiplied with inner products of your vector u with the eigenvectors, right? Now, think about this. You have a d-dimensional space, right? And then you have d different eigenvectors, v1, v2, v3, all of them orthogonal to each other, right? This is a base, right? And then you get your vector u, okay? And then you are computing the inner product of this vector u on any of them. What are you doing? You are representing u in the space of that eigenvectors, right? This is the thing that you are doing, right? And you do know that this u itself is a unit vector, right? So what would be the best span that you can do if you have this choice to play with this u? What would be the best guy that you would put there? You would, the values. You're going to put it exactly to be the one which has the maximum eigenvalue, right? Because if I just deviate from that one, So this guy, this term, is going to be smaller than 1. And my energy are going to be represented by the other bases, right? And all of them have smaller eigenvalues, right? So the output of this summation going to be smaller, right? So if I want to put it a bit in concrete words, first of all, your u being projected on any of the bases is definitely smaller than 1, right? The second thing is that when u is projected on all of these bases, when you add them up, it's going to be 1 because u itself is norm 1, right? Its projections added up is going to be 1 as well. Now you have this term. Now you have, now you have this term, and you have a bunch of numbers, all of them between 0 and 1. Each of them is getting multiplied to this guy, and then you add them up, right? And this is like averaging all of those eigenvalues, right? So you have multiple eigenvalues, you are averaging them out, right? And the weights of this averaging is your choice, right? Now, which choice is the best one? Okay, I'm going to put all the weights on the maximum eigenvalue, right? Because if I reduce that and I give it to any other eigenvalue, that eigenvalue is smaller, this average is going to be smaller, right? So this is the reason that you're going to say, okay, I'm going to put u exactly the eigenvector whose eigenvalue is maximum. Everybody's cool? You got the idea? Questions? Yeah.
Just from an intuition standpoint, so when we decompose to the covariance matrix, and u times u transpose covariance u.
Right.
Now it feels like we're taking the eigenvalues of the covariance and we're inputting it as u. Is that
Eigenvectors of, yes, eigenvectors of the sample covariance, exactly. And we set the guy who has maximum eigenvalue, we set that one to be u, exactly. This is the way that you can maximize that term, u transpose sigma u, is the solution, actually.
So it's kind of like u is out of the sigma.
Yes, you compute u out of sigma, and this is what you want to do, right? Because you want to compute u from your data, and sigma is computed directly from your data, right? No? Questions? So you can extend the same idea if you have 2, if you have 3, and so on, right? If you have 2, you're going to see that you're going to expand the same expression as before, and you see by the same lines of conclusion, you're going to conclude that u1 should be the guy who has the largest eigenvalue. u2 should be the eigenvector who has the second largest eigenvalue. Now, if you have k different u, so if you're compressing into k dimensions, then this list is going to look the same, right? The largest eigenvalue, second largest eigenvalue, third largest eigenvalue, and so on, right? So that is going to be what we call it PCA, principal component analysis, okay? And now, why we call it principal component? Because those eigenvectors, Vmax, Vmax2, and so on, these are what we consider to be the principal components of the data set, right? As you saw in this particular diagram here. So this guy, I mean, this data set has 2 bases, right? 2 components. One of them is this eigenvector. The other one is this eigenvector, right? But which one is principal? If you want to choose only one, then this is the guy, right? If you have d-dimensional space, you have your data is spanned in d different bases, right? D different directions. And how you can find those directions, just find the eigenvectors of your sample covariance, right? Now that you have those eigenvectors, which one is principal? Which one are the, say, 5 principal? The ones which have the 5 largest eigenvalues, right? This is what you call. And then you would say, if I want to represent my data in a lower dimension, the bases, the principal components that I should take are actually those principal components computed out of the sample covariance matrix. So this is going to be the algorithm. So you're going to compute mu to be the average, the sample mean. Then you compute the sample covariance. You do the decomposition. And then for the k, which is given to you as the size of your compression, you are going to set your uk, every single of those components in your compression matrix, you set that U to be the principal component, K, right? Questions? No question? Okay, so that would be this. So the algorithm sounds quite simple, right? So you're going to try it in the assignment too. You're going to try implementing it. It's quite simple. The only complexity that you have is to compute this decomposition. And anyone knows what is the classic complexity of this calculation? If your sigma is dimension d, what is the order of this computation? D cubed. D cubed. So it means like if you double your size, it's going to be 8 times more computation, right? 8 times longer. It's not a very efficient sort of computation. You can reduce it. There are 2 points, I think 2.72 is like the most efficient numerical algorithm. But anyways, still is not exponential, so it's possible to do it. No? If your data is not crazy large, you can still, large dimensional, then you can still do it, right? But if you have a data which has, I don't know, 3 billion pixels in it, because the size of sigma is proportional to the size of your data samples, right? So if it is a huge image, then it might be quite a computation, right? Okay. This is the PCA algorithm. How you can use it in practice? Well, you can use it really to do the compression. For instance, say I have this image. This is what we started with. It has 300 pixels in row. It has 200 pixels as a column. One way that you can do the compression, you could say that, well, it's a 60,000 dimensional sample, right? And I can go ahead and find lots of images. I make a data set of lots of images, right? Every single of them is 60,000 dimensional. And then you put them inside a data set. You do PCA on that. You find the principal components, right? This is one way you can do it, but this is not the typical way that we do it. The alternative way, I mean, because if in that case, if you think about 60,000, then computing this covariance matrix and doing the decomposition, it could be quite challenging. The other way is this way. So you look at your single image itself to be a data set. So you would say that it has 200 different columns, right? Each of them 300 dimensional, right? So I think of it to be like 200 different data samples, right? Each of them 300, and then you try to find the principal components of that data set. Everybody's cool? Or, for instance, you could say 300 different samples, each of them 200 dimensional, right? And you might say that this makes sense because, well, I mean, samples in one row have, or one column or one row, they have correlation to each other, right? So it's going to somehow give you the idea how smooth the image is changing over a row or over a column. Okay, you can do it this way. And if you do it this way, you can start by k equal by 0, right? If I set k equal by 0, what does it mean? It means that I am compressing everything to a constant, right? And that constant is going to be the average vector, right? And that average vector is it, right? Now, if I just represent my image by my compression, the first row, the second row, all of them are going to be the same thing, right? And if I do that, then this looks like this, right? Every row is the same, correct? You can start increasing k. You can make k to be 10, okay? And if you do k equal by 10, then you start to see something like this, right? Now it's somehow showing up the image, right? But it's not perfect. And you can keep on increasing k equal by 20, k equal by 30, k equal by 40. 50 is pretty much what you had seen, right? But you are now dropping from 300 to 50, right? 6-time compression. And you still see the image pretty much, at least from the distance you are sitting, you see the image pretty much the same, right? Yes?
So we're only doing compression along one dimension right now?
One dimension, right.
So you could theoretically do it this way as well?
But then your data sample is going to be one dimensional, right? You either take one of the dimensions at the dimension of your sample, the other one as the data set, right? You can do it either way, right? You cannot do it both the ways, right? Or, I mean, the thing that I did here is a very basic way. I mean, the other way is that you would say, okay, I'm going to break it into patches, right? And every patch is, I don't know, is a 10 by 10 patch, for instance. And I look at it as one sample, right? You can do it as well. You know? It doesn't matter. Now, so the main reason that you see the image here like this is that very good, because really the image is not that high dimensional, right? So the image of a face or image of a scene, it does not, I mean, it cannot have that huge jumps from one pixel to another. This means that even though it's very high dimensional on your computer, but in reality it's just lying on a very low dimensional manifold, right? And PCA is here capable of somehow approximating that manifold. Questions? Yeah.
This kind of reminds me of like spectral decomposition of an image.
Same
How
thing.
does it compare with it? Is it like approximating that process?
Yes, but there, I mean, you have this choice that your basis, I mean, you are here taking eigenvectors, right? And eigenvectors at the end of the day describe in low dimension, in higher dimension, a lower dimensional hyperplane, right? But if you take instead of eigenvectors some spectral functions, which are again eigenfunctions, you multiply them and you integrate them over one metric, is going to be 0, so they're orthogonal somehow. But when you represent with those functions, you're doing basically the nonlinear version of this, right? Now, you can do the nonlinear version with known eigenfunctions, right? This is what we used to do with spectral representations. Fourier transform, I don't know, wavelet transform, or all that form. Or you can even say that, okay, those functions are nonlinear and I don't know what they are. I want to learn them as well by a neural network. That is what autoencoder is, right? All of them are the same thing.
Okay.
Yeah? Okay. So now, there are a bunch of other applications for PCA, which used to be, I mean, people, PCA is a quite old algorithm. It was one of the learning algorithms which we liked because it had a very nice solution and it had lots of applications. Compression was one of that, but one other application is face recognition. And the key idea in the face recognition is that, well, if you look at the image of a face, right, it's very high dimensional. It has lots of pixels in it, right? But if you could represent it in a lower dimension efficiently, then probably those lower dimension representation is containing all the information you need about the face, right? And if you look at one camera and you change your face, right, the image itself is going to change. So that new image where you have changed, you have rotated your face is totally different from the previous image. But essentially, if you can find the regional representation in very low dimension, it should not change too much because this face and the previous face, both of them are your face, right? So this was the idea, and they tried to do the same thing, right? So you find the latent representation, very low dimensional latent representation of the image, and as long as those images belong to the same person, same scene, right, those representations should be close. And when you do it, it's going to happen, right? And this was the idea how you can do face recognition very efficiently. And many of those early devices that you look at that and they open the door, they were basically, or for finding out people who are suspicious, right, suspect of something, right? They just get the image they got from the suspect and they try to somehow find the eigenface, and then they try to match with whatever they have inside their data set, right? So that was the idea of face recognition. So if you choose that K properly, the compression size, you can efficiently represent that face or any other scene that you have. It was very popular for face because face of human being has its own unique things, right? And then if you find the right choice K, then every human being going to have its own area in the latent space, right? Or at least people who look closer, they are closer in that latent space. People who look less similar, then they are going to be far away, right? And then that was the idea. And this k-dimensional representation, this is what they called it eigenface. And like you look at the face of same person from different angles. Well, they are different. If you just get this image and you subtract pixels from this image, then obviously it's going to be large because the hair has changed, the eyebrows have changed the place. So this is going to be totally different. But when you compute the eigenface, this is going to be the same for both cases. Okay? And then that was the idea. Well, maybe we can use it. So another application was for recommendation algorithms. And the idea for the recommendation was that, well, you have this guy. He has looked into a bunch of videos, and it has given a score to a couple of them, right? For example, it has seen this particular Fight Club. This one, I don't know what that is. What is it? Aladdin. Oh, okay. And yeah, okay. But he has not seen Matrix, right? And then you don't know what's going to be his score for that, right? But you want to find out what would he like, right, to recommend. This is what Netflix does for you, right? YouTube even does for you, right? Or Amazon does for you. When you check out a couple of things and then you score them, it's going to give you some recommendation. Take a look at this one, right? And again, you can actually do it easily with PCA. For example, you would say, okay, I have this particular guy, user N, and it has for movie, his scoring is like this, like movie 1, movie 2, and so on, right? So you have movie 1, 1 score, movie 2, 1 score, and so on. So this is the way that that person is behaving, right? This is the score vector of that person. But the key idea is that, well, score vectors, even though there are tons of movies on the platform, the score vectors should not be any possible vector in that large dimensional space, because every single person has some preferences, right? Somebody who likes drama probably likes this movie and that movie and that movie, right? Someone who likes, I don't know, comedy likes this movie, that movie, and that movie, right? So once you know this person likes comedy, then you probably can guess what are the other scores, right? So this vector cannot be everything. And then you could say it has some k principal components, right? It has k principal components. There are k specific vectors, and anyone's score vector is actually a superposition of that, right? You only need to know what are those parameters z, right? And how you can find z? Well, if you think in terms of PCA, as long as you know what is u, you can just project that vector into z-dimensional space, low-dimensional space, you find z, right? That was the idea. So you have k eigen ratings, for example, and then every person can be actually represented in lower dimension, but the latent representation. And this is pretty much PCA. And you can go ahead and solve this problem the same way with PCA. So you collect as much as rating as possible, and then using that one, you're going to just find the recommendation. Yes?
In the previous slide,
yeah.
Is D like the number of movies that the one user saw?
No, it could be, but it's actually the number of movies that are on the platform, right. And you do not have all of it, right? So you actually have a sort of incomplete matrix, right? But this incomplete matrix is no problem because you do know that this is low dimensional, right? It's ill ranked. So you don't really need to know all of the entries to know what are those components, principal components. The score given by the user, right? No, you just index the movies, right? Movie 1, 2, 3 till movie 1000, right? So it's not the title, it's actually their score. Score, right. So yes, user N for movie 1 has given a score 4, for movie 2 has given a score 1, and so on.
So if you go back to the previous slide where the table is, so for example, user 2, the one who's back here, so she's got only one rating.
Yes.
I understand this example, right?
Right.
So it's like, how does the algorithm work with one data set?
Yeah. First of all, you can get a bunch of, you can get a lot of samples, right? So if I keep on collecting people, every person has seen a bunch of them, right? And then I'm going to have this matrix which has lots of rows. A lot of points there are unknown to me, but it's not important because the matrix itself is low rank, right? This is a matrix completion problem which is equivalent to PCA. So moral of the story, if I tell you there are only 2 principal vectors, okay? And then you have this matrix which is collecting all of the vectors written as a linear combination of these 2, right? Even if you don't know some of the entries, since you know that it's a superposition of these 2, you can just find out what are the coefficients from the other columns, right? And then you can fill out those remaining ones. So that is not a problem that you don't have this, but you understood the idea correctly. So this is the vector of one user, right? And there are a bunch of missing points here. Clear? Yeah? Yeah? Okay.
Is the purpose to find out the missing points?
Sorry?
Is the purpose of that algorithm to find out the missing points? Or could it
Yes, I mean, yeah, basically that's the idea, right? And you can do it again by PCA, okay? This is what I try to explain to your friend. Because, say, I mean, you don't know this one, right? But what is this number here? Is it, for example, 5 or 1, right? Now, if you do know that this guy, for example, say this is a PCA with just one eigenvector, one principal component, then this guy is a scaled version of one vector, right? Correct? Now, I cannot have anything here because if I do know that principal component, for example, that principal component, the last 2 entries are 1 and 1.5, right? Okay? Then if you look at this one and you compare it to my principal component, you say that, well, the last principal entry in the principal component is 1, here is 2, right? And this guy should be in a scaled version of this one. So the scalar is definitely 2, right? You got my idea? You see it, or?
Can I take a stab at it?
Yeah.
So essentially, the recommendation is what we imagine the user would rate that.
Right,
vector,
right,
And
exactly.
So we use PCA to get the eigenvectors, and those are essentially, let's say, if it's only comedy and drama,
Exactly.
then the principle is like this rating would be a version of the comedy and drama, and then depending on the values that we do have, we estimate.
Exactly, exactly. That's true. That's true. So everybody got the idea? Yes. It's all right. Yeah. It's all right. You go.
About the scaling.
Okay.
You don't have, so I get this, let's say the scale
Mhm.
factor, but if you don't have a value, you can't scale the missing values.
Yeah, but you use PCA to find that component, right? Principal component.
Yeah.
Now, if it is hard for you to see that you can do it directly from this one, let's say I go ahead with all the users, right? And if I can find enough number of users, actually I just need to find a bunch of them that have seen all of these 5 movies, right? Then out of that I can find the principal component, and then I can just match it to these ones to find out what are the remaining ones, right?
Okay.
You get this? Yeah? So this is like the naive way of doing it, but in principle you don't need to really do that as well. Actually, you can start from this matrix and you complete it. If you know that this matrix is just a low-rank matrix, so it's UU transpose. There is no too many choices to have 2 here, 3 here, 4 here. Yeah? But I don't want to complicate things. Just for now, I assume that you have a bunch of users. They have seen all the movies. Out of that, you can find the principal component, right? And then when your principal vector is something, for instance, the last entry is 1, then this means that this guy is 2 times that principal component, right? And then you can simply complete the remaining ones, right? Here, this should be exactly the guy, right? So I can just get the principal component and fill these guys, right? This is when you assume that you can get the principal component. Now you might think that I need to have at least a bunch of guys seeing all the movies to be able to do that. Well, it's not the case. If you again do a bit of linear algebra, you can see that even from this incomplete data, you can find out what is the principal component. Okay? Yes?
What do you mean by categories?
Sorry?
Do you need to characterize the movies first?
No. I mean, this is the key thing that the principal component is doing. So it's going to give the same weight to those who are in the same category, right? Like somehow out of data it understands that this movie and this movie both of them are drama, and anyone who likes this is going to like this one as well.
So can I say, let's say you have the 3-2 right there.
Okay?
Yeah, 3-2, and then you don't know the movie, like what would he rate the, maybe the third movie?
Yeah.
And then you see a principal component of the third movie rating being like 4. So could we say that most likely she's going to rate as 4 for that movie?
This is not the way that you do it. I mean, you have lots of samples, okay? And you find the principal component. Principal component is going to be, again, a vector of size 5 for you, right? Because your data is now of size 5, right? This is your first sample, 1, 2, 3, 4, 5, a vector of size 5, right? Now you have a lot of those guys, right? But you assume that you can represent them in one-dimensional case. Like you can compress it down to 1, right? So this means that any guy you see here is essentially one coefficient multiplied by a principal vector, right? That is the principal vector, principal component, right? Now, if you can find that principal component, say the last entry of your principal component is 1, right? Now, if you assume that this guy is one scalar multiplied by that, you don't care that you don't know these entries, right? You would say that a scalar should be 1, right? To match this, this equation, right? Same thing here. You would say, okay, the last guy is 2, right? So it's 2 times the last component there, entry there, right? So it should be 2 times the principal component. You get the idea? Yeah. Questions? Yeah. Which one? This one? Okay. Okay, okay. Which one? These? I mean, this one. Down there. This is by decomposition. So you just do the eigenvalue decomposition. To find the eigenvalues, you need to just you compute first x transpose. This is going to be a 2 by 2 matrix. Then you write down the the characteristic equation. And out of the characteristic equation, you're going to find the eigenvalues. Then you can do the decomposition. But maybe I can explain it later on, because I just want to finish this part. But this one, you also practice it in, I guess, assignment 1. If you just check assignment 1, there we can do but on Python, for instance, you can just read a function or give this sigma to a function, and then that function is going to do it for you. Okay? So it's an algorithm. You need to run it. But I mean, these values you find out of the characteristic equation. And then you can compute this one by Gaussian elimination, something like that. Okay? Okay, so just quickly, because James is here, so I just want to finish this part. So that was the idea of the recommendation system. And it was actually, it won the 1 million prize by Netflix in 2009. So they saw that, well, you can just represent everything in lower dimension. The team won this prize using PCA, the idea of PCA, to solve this problem. Okay, so that's pretty much this. A few things that I wanted to just mention at the very end. The first thing is that PCA is quite sensitive to the scaling. So what does it mean? It means that if you have your data being shown in 1 unit, for example, look at these samples, and these samples are data when your horizontal axis is, for example, presented in centimeter, right? So x-axis is showing the height, and it's in centimeter, right? Now, if you do not change the y-axis, but you change x-axis into meters, right, you might see something like this, right? Because it's going to shrink, right? And once you change the unit, then the eigenvalues proportional to each eigenvector could change, right? And this means that your principal components could change, right? This is why PCA is known to be sensitive to the scaling. And the best way to deal with it is to always have your data normalized first. So you have your data normalized, and then you work with the normalized data. That is going to be more robust. This is the first thing. The second thing is that PCA is a linear algorithm. This means that I can go from 2 dimensions to 1 dimension if my points are lying on a line, right? But here, when you look at this particular case where the points are on a circle, I can still represent it with one single parameter. What is that parameter? The angle, right? So if I want to know what is this point, as long as I know this is on a circle, I just need to know what is the angle, right? And then I can represent that point. But the point is that this is not linear, so PCA is unable to do that, right? If you want to do this, well, there are solutions for that, and this is what we call the autoencoder. So autoencoder essentially does what PCA does, but this time it does it with assuming a nonlinear model. So it does not assume that z is represented in a linear form in terms of x and vice versa. You assume that z is computed by a nonlinear function from x, and then you can get back from z to x, or approximation of it, by a nonlinear function. And those nonlinear functions are going to be neural networks. You train that. This is going to be autoencoder. One last thing is that, as I told you before, anything that you do in at least this course, you can always interpret it in terms of maximum likelihood estimation. Now, PCA itself is a maximum likelihood estimation. So what you assume there is a latent space. And this latent space is normally distributed with mean 0 and unit variance. Okay? This is the assumption. Then any data that you see, any of those samples you see, any of those images you see, it had its own latent z. You sample it, then you put it on a line. It means that you get that sample z, you multiply it by u, you add up one bias to it, right? You put it on a line. Once you put it on a line, there is one error term or innovation term, whatever you want to call it. This guy is again Gaussian, right? It's again added to this guy, and this is what you see as your sample. Okay? So what does it mean? It means at the end of the day that you assume your x is Gaussian distributed. Those samples you are seeing around you, those images, are Gaussian normally distributed. The mean value is exactly mu, and the covariance matrix is something like this, right? And now what you want to do, you want to fit this model perfectly to the data that you have. What you can do? Maximum likelihood, right? You compute the likelihood and the data set that you have, and then you try to maximize it, exactly like what we did in the last week. If you do this, you're going to see that, I mean, this is a Gaussian maximum likelihood. We actually solved this problem. If you go ahead and solve, I mean, just look at this guy, put these terms inside the Gaussian maximum likelihood, and try to find out what is mu and u, you're going to end up exactly with the same thing that we have done here. And this is because, as I told you, anything that you do at the end of the day, somehow you're trying to learn the distribution of data, and it's only the kind of model. When the model changes, the story changes a bit. The final result changes. But the idea, the method that you're using is always maximum likelihood. Okay? Now, here, again, what we are assuming x is generated by a Gaussian or from a Gaussian random variable by a random process. And that random process is actually processing the original latent in a linear form, right? Now, what if we assume that it's processing it in a nonlinear form? It's going to be autoencoder. Now, some of you might have had seen variational autoencoder, and it's going to sample one z, Gaussian. It passes through the autoencoder. It adds the random noise. You see the image, right? And they say, we are generating the image, right? It's basically doing this, but instead of having this linear model simple in PCA, it's just putting a neural network there. Okay? So actually, if you can do this efficiently by variational autoencoder, you can start generate images, right? Because you learn what is the right function here. So then you want a new image. You randomly choose one Gaussian z. You pass it through your function. You get something. You sample from the output. This is going to be the new image, right? The one you have not seen before. Everybody's cool? Questions? So if you got no question, you can take a look here. That was pretty much this for PCA. We are over roughly with the unsupervised learning part. So next week, I might do a quick recap and give you a few final notes. And then we're going to start with linear regression. Okay? Question?